Hi everyone, this is a lesson about slope fields, and a slope field is a way to graphically represent the solutions to a first order differential equation. So let's take a basic equation, dy dx is equal to x. We know that if you solve this equation, you would find a family of curves y is equal to x squared over 2 plus c. So this family solves this first order differential equation right here, okay? So what if I wanted to graphically visualize this? What I could do is take this differential equation and use it in the xy plane to draw a little local linear tangent line at every point on the plane. So for example, at 0, 0, x is equal to 0, so I would just have a little tangent line with a slope of 0. Actually, that would be the case for any point along the y-axis, because for all of those points, x is equal to 0. If I went over to x is equal to 1, I would go dy dx equals 1 means, or dy dx equals x means dy dx equals 1. So I would get I could draw little tangent lines with a slope of 1 over here. And then I could go to other points in the curve and do the same thing. At every point in the curve, I'm drawing a tangent line to the solution curve, right? These are not the solution curves. These are just the slopes of the solution, the dy dx. And just to draw a couple more, if I were here at -1, then my slopes would have to be -1. So I could draw -1 for the slope. So any solution passing through an x equals -1 would have to have that slope. So now if I connect these tangent lines, I know that the solutions are differentiable. This right here is a differentiable function. It's locally linear, so it's going to look just like its tangent line at every place. And so I can just follow these tangent lines, and I would know the direction of my solution curves. And the solution curves would then look just like y is equal to x squared over 2 plus c. So this is the idea of a slope field, and you just saw that I calculated the slope field by calculating dy dx at various points in the xy plane and then drawing a short line with the calculated slope at each xy point. Connecting the line segments then gives us the solutions to the differential equation, because the line segments are tangents to the solution curves. Each differential equation has many possible solutions, as you know. So here, x squared plus c means all of these blue parabolas are solutions to this differential equation, and the only thing is changing is, the vertical shift. All of those parabolas, an infinite number of them, solve this differential equation. But if we were given a specific point using an initial condition, so if we were given an initial condition, say we were told that on this differential equation we were just talking about, if I said, I want you to solve this with the initial condition that f of 0 equals 1, then I'm saying, well, I want that particular solution curve that goes through this point at 0, x equals 0, y equals 1. So I want to be at this point, and then from there, I want to draw my solution curve. Well, you'd follow the direction of the tangent lines, and you would get a specific curve that goes through that particular point. And that would be the particular solution to that differential equation. Okay, so now the first thing we need to know how to do is to sketch a slope field for a differential equation. So here is the differential equation y prime equals y, which means dy dx is equal to y. So what we're saying is that at any place in this xy plane, the slope is equal to the y value. So that means along the x-axis where the y value is 0, my slopes would all have to be just flat lines, slope 0. Remember, this is slope 0. So when I'm drawing a slope 0 line, that's what I'm drawing here, okay? Then if I were at x is equal to, y is equal to 1, then my slopes would all have to be 1. So if I'm up here going through this horizontal, anywhere on this horizontal line where y is equal to 1, the slopes would be 1. If I were down here at -1, then my slopes would have to be -1. So this is how you generate a slope field, and you do it for however many points the question asks. In this case, it didn't specify. So I'll just draw a few more. As you go higher and higher, say you're here at y is equal to 5, then the slope has to look much steeper. It's like a slope of 5. That would look something like this, okay? So I'll draw a few of these, much steeper as I go up. And then if I went even further, then they almost look vertical by the time I get to the top of this, because they would have to have a slope of 10, which is almost like a vertical line up there, okay? So this is how you generate a slope field. Now, let's see how you draw a particular solution. So when we're asked now to sketch the solution to the initial value problem, the same differential equation, but y of 0 is equal to 1, then you go to the point 0, 1, that's the point that you're given, and then sketching the solution means following the slope. So remember, these slopes are the tangent lines to the actual solution. So the actual solution is going to look something like this, right? You keep following the slope and you kind of curve in the direction of the tangent lines as you hit them. Recognize that along the x-axis, this particular differential equation, if you started at any point along the x-axis, like say over here, the slope is 0, and so you're going to get a solution that literally is just the x-axis. In other words, y is equal to 0 solves this particular differential equation. And I'm saying that because as you extend your green solution, which is the one we want, the one that goes through 0, 1, to the left, you want to make sure that you do not cross the blue solution curve. The solution curves to differential equations do not cross each other. So we're going to have a solution that looks like this. And the interpretation is, as you think about like what is the slope when you're very close to 0 on the y-axis, say you're at 0.1, the slope here would be almost flat, right? It would be like this, the slopes. And as you get closer and closer to the y-axis, the slopes are getting flatter and flatter, and that's why the green graph looks the way that it looks. Recognize that there's lots and lots of other solution curves that are sitting in this xy plane, infinitely many, but the initial condition pins you down to one specific curve, which is the green one. Okay, let's sketch another one. So here we have dy dx equals x. So in this case, my slope field is going to be my x value. So that means if I go up and down at any x value, the slope shouldn't change. So here, for example, it's going to be 0 all up and down the y-axis. And then if I go to x is equal to 2, then it'll be 2 all up and down that line, because x is equal to 2. Y doesn't even come into play in this particular slope field. So it would look something like that. If I'm at x is equal to -2, then the slope is -2. And again, y does not come into play. So up and down, there's no change in the slopes. So it looks something like this. And we already talked about how this particular equation, we know the solutions are this family. And so as you draw more and more of these slope fields, you're going to see that, that's really what, when you connect these lines, they make that pattern of the family of curves x squared over 2 plus c. So let me see if I can show you that by drawing just a few more of these slope lines. So here now I'm at x is equal to 4, so I'm making the slopes steeper. And then you can see that if you start at any, well, let's see, we have here, we're trying to sketch the solution at 0, 1. So if I were doing that in blue, then I go to 0, 1, which would be here. So let me just draw in the slope there would be 0, like that, okay? So I'd have to start there and then follow that and think about as I'm going, as x is getting bigger, the slopes are getting bigger, and so it's going to end up looking something like this. And then on the other side, it's getting more and more negative, so there it's going to look like that. So that's the specific particular solution to this initial value problem, but recognizing, right, that there are just an infinite number of solutions to this differential equation. Okay, so let's sketch a slope field for this equation, y prime equals x plus y. So you want to just think about your x and y coordinates. Here at the origin, both are 0, so their sum is 0. Then at this point, it's 1 comma 0 is my xy point. So the slope is going to be x plus y, which is 1. Here I'm at 2, 0, so the slope is going to be 2. Here I'm at negative 1, 0, so the slope's negative 1. And here it's negative 2, 0, so the slope is negative 2. Down here I'm at 0, negative 1, so the slope is negative 1. Here I'm at 1, negative 1, so the slope will be 0. And then here I'm at 2, negative 1, so the slope will be 1. So you just go in this way and you calculate all of your slopes. Here I'm, for example, at negative 2, negative 1, so the slope will actually be negative 3. So the way I make it steeper is by just aiming for a 1 over 3 up, kind of like that. And I just aim for a rise over run of 3. I don't make the line all the way out to there, but I just aim for that when I make my little line. Okay, and then here I'm at 0, 1, and so this will be a slope of 1. Make that a little better, aiming for here. And then here I'm at 1, 1, so I'll have a slope of 2. And then here I'm at 2, 1, so I'll have a slope of 3, and so on. So you can just pause the video and complete this and then check your answer. Okay, so your slope field should look something like that. Okay, so part B here says let y equals f of x be the particular solution to this given differential equation with f of 0 equals 1. So what we're being told is that this equation obviously has an infinite number of solutions, but we want to visualize first. They didn't ask us to, but let's first visualize this particular solution that goes through the point 0, 1. So that's here. So I have to start at that point and then go with slopes, draw the solution curve following the slopes, and recognize the slopes are increasing as I go out this way. So I'm going to get something like this. Here, as I come in along, if you look here along all of this line, we have slopes 0, right? Because whenever y equals negative x, then the slope is going to be 0. So I have to make sure I have a slope of 0 here, and then slopes are going to get more negative, but they're never going to become more negative than 1, because if you look carefully, you have this line here where all the slopes are negative 1. So that means that this line is a solution. This line y equals negative x minus 1, that green line is a solution. So as I draw my blue solution, I have to remember I'm not allowed to cross that green line because solution curves never cross each other. So that's the blue solution curve, is the particular solution here that goes through 0, 1. And then in the next part, we're asked to write an equation for the line tangent to the graph of this solution curve, this particular blue curve we just drew, at x is equal to 0. So that means we're writing the equation of this particular tangent line. So that's easy because we know that we have to go through the point 0, 1. We know the slope is given by the differential equation, right? dy dx equals x plus y, so dy dx equals 1. And so then the equation of that little black line, or that black line, is y minus 1 is equal to m times x minus 0. So y minus 1 equals x, or if you want to say y equals 1 plus x, that's the tangent line equation. Now, if we're using this equation to approximate f of 0.1, this is a linear approximation. What we're saying is we're really talking about the y value on this blue curve. That is what f of 0.1 is. It's some y value in there. But let's use this black graph to get that y value. So this is our linear approximation that we learned about back in the fall, and we know that the linear approximation L of x is f of a plus f prime of a times x minus a. So let's just be clear that our point is the a f of a. So in this case, the point where we drew the tangent line is 0, 1. And then our f prime of a is the slope at that point. So it's f prime of 0 in this case, which was 1. So we'll use that here. Our linear approximation equation is L of x is equal to 1 plus 1 times x minus 0. It's that tangent line equation. And then if I want to do L of 0.1, it's 1 plus 1 times 0.1, which is 1.1. So we're saying that this y value on the blue graph, f of 0.1 is roughly equal to 1.1, which is the y value at 0.1 on the black tangent line. So we can end by saying f of 0.1 is approximately equal to 1.1. Okay, here's a second example, same type of problem. We're sketching a slope field for this differential equation at the 6 given points. So the equation is y squared divided by x minus 1. So you can even make a little table if that helps you for the points. So we've got 0, 0, 2, 0, 0, 1, 2, 1, and 0, 2, and 2, 2. Those are our points. And then this equation becomes 0 divided by negative 1, which is 0 for the slopes. Y squared 0 divided by 2 minus 1, that's 0. Here I have y squared is 1 divided by 0 minus 1, that'd be negative 1. And then I have 1 divided by 2 minus 1, that would be 1. And then I have 4 divided by 0 minus 1 be negative 4. And then I have 4 divided by 2 minus 1, which would be 4. And so then I can just come and draw my slopes here. So I'd have slopes that look like this. 0, 0 is 0, and this is 0. And then 0, 1, my slope is negative 1, so that would be something like that. And then 0, let's see here, 2, this is 2, 1, my slope would be positive 1, so something like this. Let me do that again, something like that. And then 0, 2, my slope is negative 4, so that's going to look pretty steep, something like this. And then at 2, 2, I have a slope of positive 4. So that would be my little slope field there. Then they say let y equals f of x be the particular solution to the given differential equation, that one, with f of 2 equals 3, right? So this is an x value, this is a y value. And we're writing our tangent line equation. So my point is that point, 2, 3. My slope is going to be dy dx at 2, 3. So I have to put that into the equation, and I get 9 for y squared divided by 2 minus 1. So it's 9. So that's my slope. So the equation will be y minus 3 is equal to 9 times x minus 2. And then for the linear approximation at 2.1, my point is again 2, 3. My slope, so this is my a, f of a, and my slope is 9. This is my f prime of a. So then the linear approximation L of x is going to be f of a, which is 3, plus f prime of a times x minus a. And if I'm trying to approximate 2.1, then I just put in 2.1 into the linear approximation equation, and I get 3 plus 0.9, or 3.9 would be my approximation. Okay, so a lot of questions are going to involve matching a slope field to a differential equation. And so I want to go over some strategies for that and then practice some questions. So let's take a look at this table. So here we have a differential equation which only depends on y. So when you have a case like this, then as you move left and right, you should not see any change in your slopes. So if the differential equation only depends on y, then slopes along horizontal lines will not change. If your differential equation depends only on x, like here, right, then slopes, if you move up and down, it's y that's changing, but that doesn't affect the slope. So you should see exact same slopes along vertical lines if the differential equation depends only on x. If the differential equation is something like dy dx equals xy, right, now we can think about the signs of x and y in the different quadrants. We know that depending on the quadrant, we have a certain pattern for the signs of x and y. And if you're thinking then of the sign of something like xy is going to be positive in the first quadrant, negative in the second, positive in the third, and negative in the fourth. So if your differential equation looks like this, then you're going to see only positive slopes in quadrant 1, negative slopes in quadrant 2, positive in quadrant 3, and negative in quadrant 4. That means all the little lines be going like this in quadrant 4 versus in quadrant 1, they'd be like that. They'd be different values, but they'd be all positive, okay? Something like this, dy dx equals x squared plus y squared. This is always positive. So you should be seeing the whole xy plane have positive slopes. All the little slope lines should be positive. If you have something like this, dy dx is x squared divided by y, well, the top is positive, right? And the bottom here can be positive or negative. So when y is positive up here, all the slopes should be positive, right? They should all be positive. And then when you're down here and y is negative, then all the slopes down here should be negative. They can be different amounts of negative, but they will be negative. So above the x-axis here would be positive, and below the x-axis would be negative. If you had dy dx is now negative x over y, right? X over y will follow the same kind of pattern as xy. It's going to be positive here because of x and y both being positive. Here it's going to be negative. Here's going to be positive. Here's going to be negative. But now if you tack on a negative here, then this particular negative x over y is going to be negative here and positive here and negative here and positive here, okay? So you can use these type of strategies when you are trying to figure out a matching problem. So let's practice some of those. Here's one. Here's a matching problem. We're matching this slope field to these differential equations. So when I look at these, I can already see that everywhere I look, the slopes are positive. They get to 0, but they're always positive, okay? So that is telling me that something like this is not going to be an answer to that slope field. If I look at something like this is also not going to be an answer here because xy would be negative in the second quadrant. If I look at something like B, this also, remember this is the one which would be all positive slopes above the x-axis and all negative ones down here, so it couldn't be that one either. So it must be this one, all positive slopes here. Then I can go further and kind of check that it makes sense. When x is 0, yeah, it looks like I've got 0 slopes here. And then as x gets bigger, my slopes get bigger. So yeah, that totally makes sense, and the answer would be C. Okay, this next one here, we're matching to a differential equation. I want you to notice the pattern that you see. You can kind of see it's like a water pattern or a wind flow pattern. You can see that the solutions here, when you connect these slopes, look like they're circular, okay? So those are the solutions. Here we're asked to find the differential equation. So, I mean, if you thought of it that way, you could think if the solutions were circles, then they would have to be something like this, and you could kind of work from that to get the differential equation. So that would be one way to go. But another way to go would be just to think through the strategies we just talked about. So here, this is all positive. All the slopes would have to be positive. I can see that some of my slopes, like here and here, are negative. So it couldn't be A. This one right here would have to be positive in the first quadrant, negative in the second, positive in the third, negative in the fourth. And let's see, these slopes are negative in the first quadrant, so that one's out. This guy would have to be, C here would be where the differential equation doesn't depend on x. So that means when you move left, right, then you should be having exactly the same slopes. But here, as I move, say I pick a certain y value like 2 and I'm moving across, my slopes are changing, so it couldn't be this one. So it looks like this better be our answer. Let's think about that. X, y would be positive in the first quadrant, but this negative sign is going to make it negative, and then positive, negative, positive. So let's just check our slopes. Yeah, that looks about right. Negatives here, and then positives here, and then negatives here, and then positives here. So that checks out. Let's think about some specific points. That's another way also to establish a connection between the equation and the slope field. So just pick a point like 1, 1. So then dy dx would have to be negative 1 over 1. So let me check. If I go to 1, 1, so here's 1 and here's 1. Now, there isn't a slope line drawn exactly there, but you can see that if you were to think about, your solution curve passing through there, you can see it does have a slope of about -1, okay? You can also pick a point that you're given that the slope field is actually drawn for and check there. So you can also see that when y gets to 0, we're getting here y is equal to 0 is the x-axis. You can see that the slopes are getting more and more vertical as you get to cross the x-axis, and they're getting more horizontal as x is 0. So that all checks out with this answer right here, D. Okay, I want to show you this problem though to help you realize that sometimes the matching that you're doing will be not to the differential equation but to the solution. So notice these answers are all y equals something, right? So they're not dy dx that you're matching to. You're matching to the solutions. So when you see this slope field, you can picture the solutions, right? You can just draw that wind pattern that you would get if you just followed these slopes. And that would look something like this. And from that, you might be able to guess that the solution shape has to now look like some kind of a graph that would have that kind of shape. Well, y is equal to x squared looks like that, so that doesn't seem right. Y is equal to e to the x looks like that. That doesn't seem right. E to the negative x, no. Cosine x, no. Ln x seems to be the closest one, right? So that would be one way to get our answer, which is E. Another way would be to do the dy dx and then check the slope fields, right? So you can also do this, and you could realize from this that when you do any of the other ones, like for example, y prime is equal to e to the x, if y prime were equal to e to the x, then as you go out further with x, the slope should be increasing, but these slopes are decreasing as x increases. Same thing with 2x, right? It couldn't be this, it couldn't be this. Sine x, I mean, that would be slopes that are increasing, decreasing, increasing, decreasing. That doesn't seem to be happening either. E to the negative x should be slopes that are decreasing because of the negative x. So that does seem to be happening as x increases, the slopes are decreasing, but they should all be negative, and these slopes are all positive. So it's not that. 1 over x, yeah, the slopes are decreasing as we go with bigger x's, but they're all positive. So it again points us to this. Okay, so that's something to pay attention to. Are your choices that you've been given the solution curves or the differential equation? Okay, here's some more matching problems that we're going to do. So we've got 6 slope fields and 6 equations, and we have to match. So this is how I would think it through. There's a lot of different strategies we can use, so I'm just going to tell you how I would do it, and I'm sure you guys are going to come up with some amazing strategies for yourself. So when I'm looking at this, I might pick the simplest one, 45 here, and think, okay, these are all positive slopes. They should also be increasing as x increases to the right, and they should be decreasing as I go. Decreasing means more and more negative as I go to the left. I should have 0 slopes all up and down the y-axis. So if you think of all of these conditions, just using the 0 slopes on the y-axis, I could say, well, it would have to be A or B. And then if I'm thinking that the slopes have to be all positive, then it would have to be B because A has negative slopes. So I think that 45 goes with B. Also notice that there's the symmetry. If it's absolute value of x, then the slope for this side should be the same as the slope for the other, symmetric x value. Okay, so that's 45. That one is B. Let's take a look at dy dx equals xy. We talked about this one in terms of the quadrants. So I should see positive, negative slopes. So let me see. I'm just looking at these going, well, which one could that be? This one has positive, negative, positive, negative. So I guess it could be this one. XY would mean I need zero slopes all along the y-axis, and it looks like zero slopes all along the x-axis. So that checks out. I can check some points, like I can go, if I say 1, 1, the slope should be 1. So here, by the way, they told us that this window is negative 6, 6 by negative 4, 4. So this right here is negative 6 and negative 6 here. So 1 is probably, 1, 2, 3, 4, 5, 6, somewhere here. And I can see that up here, it's negative 4, 4, 1, 2, 3, 4. So if I'm here, I am seeing the slope is 1. So that would be another thing to check out. I'm going to go with 46 is A. Okay, then we have these two, 43 and 44. Those should also be all positive slopes. So if I look for all positive slopes, well, let's see here. I would say, are they all? Looks like they're all positive, the remaining ones. So maybe that doesn't help very much. So let's think a little bit more. If we're thinking about x minus y, now this would be another thing, a trick you can use is this is going to be 0 when x is equal to y, right? So along the line y equals x, I should be seeing 0 slope. So if I look at these pictures carefully, this is the only one where along the line y equals x, you can see that my slopes are 0, 0, 0, 0, right? So I think that's the giveaway. That one is going to match to C. 44 is going to match to C. Here, similarly, x plus y equals 0. That's going to happen along x equals negative y or y equals negative x. So I should see a line of 0 slopes along y is equal to negative x, and I do with C. So this I'm going with C. Okay, so this is 43. This one, oops, I said C when I meant E for 44. This one's 44. We got 45 already, and I think we said 46 was A. So we're left now with D and F, and we're matching to these weird square root ones. So here, all the slopes should be positive for both of them, and they are. Here, let's see, if I put in, for example, x is equal to 0 in 41. If I put in 0, then for 0, 0, I should have a slope of 1 for 41. So I'm looking here at my two graphs, and I think this one looks like a steeper slope than 1 down here. This one looks promising. That looks like it's about 1. So that's one thing to check. What else would I check? I could check that as x gets bigger, these slopes get bigger, and they certainly do get bigger. I could also check that I could put in some other points. I could put in x is equal to, I could put in another point like maybe along the y-axis 0, 1. These slopes, I forgot. Yes, these are all just x's. So this should be like up and down the vertical lines. These slopes should not change. So when I look at this graph right here, right, I can see that up and down a vertical line, any vertical line, these slopes are not changing. So this one is going to go with that equation 41. The other one here, notice, you can put in 0, 0, and you would get that the slope should be square root of 5, right? So steeper, it's, more like 2 point something. So that checks out with that slope there. You can also see that these slopes are only changing along vertical. They do not change along horizontal lines. So if you look along a horizontal line like this, you see the exact same slope. Why is that? Well, there's no x in this equation, so that's why. So this one right here is going to go with 42. Okay, so hopefully that helps with some strategies how we match slope fields with their equations. So I hope you enjoyed that. Slope fields are really fun, and yeah, have fun doing the homework, and I will talk to you soon.